we are going to cover stoichiometry. We're going to talk about the concept of limiting and excess reactants. This is a pretty big deal in AP chemistry. We have to determine in a chemical reaction if there is one of the reactants that has a smaller amount and runs out, then that's what controls the reaction. And so in every reaction, every type of reaction, except for decomposition, we have to make sure that the question is asking us about limiting an excess reactant. Most of the time in AP chemistry, they will mix these into other complicated problems, and we have to understand what those terms even mean. So just for basic definitions, limiting reactant is a substance that controls the quantity of the product that can form a chemical reaction. An excess is what is left over and not completely used in a chemical reaction. So let's say that I added vinegar and baking soda to each other, and they make the products. Well, one of those is going to be the limiting reactant, and one is going to be the excess reactant. The limiting reactant runs out, reaction stops, and it's going to be able to make a certain amount of product. The limiting reactant is used up, but there's going to be a little bit of the excess reactant left over because the reaction stopped and there wasn't enough of a limiting reactant. And so in our stoichiometry problems, we're going to have to be able to figure out which one is which, and it takes some math calculations. It takes some conversions using mole ratio. When we do the calculations, our answer is going to be what we call the theoretical yield. Yield is saying how much product. So theoretical yield is the quantity of product that could be made if the reaction worked perfectly. The limiting reactant is going to be the thing that makes the theoretical yield. And so whenever we're doing these math problems, we're also trying to identify what is the theoretical yield. To do this, we have to do two conversions. We have to do two stoichiometric conversions. We have to convert both of our reactants to the same product in the same unit. Whichever answer has the smallest amount of product, that's the theoretical yield. The reactant that made that smaller amount of product is your limiting reactant. The other one is your excess reactant. There's also something called actual yield. Actual yield is if we were in lab and we measured out a chemical reaction, the actual yield is how much was actually made. Your actual yield is always going to be lower than your theoretical yield, because theoretical is if the reaction was perfect. So nobody accidentally spilled anything, water didn't stay behind in a beaker, all the equipment was working perfect. So our actual yield is always going to be slightly less than our theoretical yield. Percentage yield is an efficiency calculation in chemistry. We do actual over theoretical times 100, closer to 100% yield. That means that we are able to get all of our material back. Further away, that means that our reaction is not very efficient. So let's do a couple stoichiometric calculations. For limiting and excess reactant problems, you have to do two stoichiometry conversions. You have to use what the problem gives you and do your conversions. So in this one, the equation is already balanced, so that's nice. We don't have to balance it. Whenever I have a balanced equation, often I go ahead and underline the coefficients, and I fill in my ones, if I could write. So I have one P4 there, I have 5O2, and then just a understood one P4O10. So down here, we're going to start our problem. So one of my givens is 0.202 moles of P4. And my other given is 1.56 moles of O2. When you do limiting and excess reactant problems, you have to use both reactants. This is a synthesis reaction because I have two reactants in one product. And so I'm going to convert both of my reactants to the product. And it specifically says that I have that much for my reactant says determine the theoretical yield in moles of P4O10, limiting reactant and excess reactant. So what I'm trying to get to, my unknown, is moles of P4O10. So down here, I'm going to put mole of P4. Remember when we are doing mole ratio, we look back at the balanced equation. This is going to be 1 mole. And I'm trying to get to moles of P4O10, so it's going to be 1 mole of P4O10. Down here, we're doing oxygen. So whatever in dimensional analysis, whatever I start with, I got to cancel with on the bottom. So I'm going to do mole of O2. You can go back up to the balanced equation. There's a 5 in front of it, so we're going to write 5. And we are also still trying to get to the same product. At the end, you should have the same product in the same unit, okay? So 0.202 times 1 divided by 1 is just going to give me 0.202 moles of P4O10. But then the other one, I can't do mental math with that one, so I'm going to do 1.56 divided by 5 in my calculator. It comes out to 0.312. This has 3 sig figs. My answer also needs to have 3 sig figs, so it's going to be 0.312 moles of P4O10. That's step 1, is convert both of your reactants to the same product, same unit. Then you look at the 2 numbers. You decide which one of these numbers is the smallest number. 0.202 is smaller than 0.312. So I typically tell my students to circle it. This is my theoretical yield. Whatever made my theoretical yield, which was P4, that is my limiting reactant. O2 is my excess reactant. So what happens in this reaction, and what we just did, is when we combine 0.202 moles of P4 and 1.56 moles of O2, the 0.202 moles of P4 is going to run out. The reaction stops, and this is the only amount of product it can make. I'm going to have some leftover oxygen after the reaction stops. Use up all my P4, leftover O2. But this number is never attainable, because when this P4 runs out, it can't get any more than 0.202. So when you do these problems, whichever number is the smallest, that is your theoretical yield. Whatever makes it is your limiting reactant. The other one is your excess. So let's do it again. This time the stoichiometry is going to be a little bit more complicated. So in this one I have 6Na, 1 Fe2O3, 3 Na2O, and 2 Fe. This is a single displacement reaction. It's a cation single displacement. Sodium displaced iron. Iron went and hung out by itself, and sodium bonded with oxygen. We are still going to have to convert both reactants to a product in the same unit. So it says if you start with 100 grams of sodium and 100 grams of Fe2O3, what is the theoretical yield in grams of iron, limiting reactant, and excess reactant? So again, we've got to do 2 conversions. So we're starting with 100.0 grams of Na and 100.0 grams of Fe2O3. So last one was a mole to mole conversion. So it was 1 step. This is a gram to gram because it wants it in grams of iron. So this one is going to end up being a 3-step stoichiometric conversion. Okay, so if I start with grams of Na, I have to cancel with grams of Na. This is going to come from the periodic table, and that periodic table is going to be the AP version, is the one that I recommend using because that's one you guys are going to use on the AP exam. On that one, the mass of sodium is 22.99. Dimensional analysis makes us cancel grams of Na with grams of Na. Based on the definition of molar mass, grams is always equal to 1 mole of that substance. That's step 1. Step 2 is I got to convert this was the whole point of this one, was get it into the common unit of mole. My second step is to try to do the mole ratio from our balanced equation. So I start with mole of Na. So I'm going to do mole of Na. This comes from my balanced equation. It is 6. When I use moles and I'm dealing with grams and moles, the only time I can use the coefficients is in my mole ratio step. Grams is always 1 mole. This step is going to be where I look at my balanced equation. I'm trying to get to grams of iron. I cannot go straight to grams, but I can go to mole of iron. This is how I switch from my known to my unknown. It has a coefficient of 2. So now I've canceled my moles of Na. I have mole of Fe. That is going to be 1 outside of this ratio. It is always 1 no matter what. And I'm trying to get to grams of Fe. And from your periodic table, that's going to be 55.85. Okay, I'm going to go ahead and calculate this one out, and then we're going to do our other conversion. So any number on top you multiply by, any number on the bottom you divide through by. So I'm going to do 100 divided by 22.99 times 2 divided by 6 times 55.85. And it comes out to, I need 4 sig figs, it comes out to 80.97 grams of Fe. Again, sig figs come from your given. I have 1, 2, 3, 4 significant figures. So now let's do the same thing down here. I'm going to cancel with grams of Fe2O3. This comes from my periodic table, but this time I got to do 2 times the mass of iron plus 3 times the mass of oxygen. I got 159.7. And then up here I have 1 mole of Fe2O3. I didn't finish marking out my stuff over here, did I? So then this is going to be, that is canceled out. So now I'm going to go mole of Fe2O3, which is 1, goes on the bottom. And the rest of the problem is going to be the same because I'm going to the same product. So I'm going to do 2 moles of my unknown, which is iron, 1 mole of Fe on the bottom, and 55.84 or 85 grams of Fe on top. So I've canceled that. I've canceled that. I'm going to be left with grams of Fe again. So now let's calculate that out. So 100 divided by 159.7 times 1, times 2 divided by 1 times 55.85 divided by 1. This time I get 69.94. Because again, I need 4 sig figs. So now that I've done all the math, I have to look at my answers. Which answer is smaller? 69.94 is smaller. This is going to be my theoretical yield. Fe2O3 is my limiting reactant. And that makes Na be my excess. So you need to become pretty comfortable with understanding how many steps you need to have for your stoichiometric calculations, also getting comfy with doing this process twice. In AP questions, this is usually not the end of it. Usually you have to figure out what the limiting is and then do more with that. So you guys want to be sure that you are confident in your calculations to get to those final answers, that you can identify which one is theoretical yield, limiting and excess. Be super careful with your masses, especially if you're adding a mass for a compound, because if I had accidentally added this mass wrong, then whenever I came over here, this number could have been wrong and it would have made me identify the wrong theoretical yield. So be real careful on these stoichiometry calculations. And that's it for today's lesson. Be sure that you go back and become comfy with knowing how many steps. This one was just a 1 mole. Or 1 step because it was mole to mole. So I start with moles, I went to moles. It's just the mole ratio step from the balanced equation. Sometimes it could be a 1, 2, or 3 step calculation. You just have to figure out which one it's going to be.